This video is going to focus on naming rules for compounds. In this course, we are going to deal with three different types of compounds that can largely be differentiated by what they begin with. So here we find that this compound starts with a metal, qualifying it as an ionic compound. This compound here starts with a hydrogen. It's going to be an acid. This one starts with a non-metal, which means it's going to be covalent. So this video is going to focus on these three different types, and amongst these three kind of larger categories of compounds, we're going to find that there's even some kind of nuances within them. So let's first start by taking a look at ionic. Within ionic itself actually has three different types. We find something pretty straightforward, just a binary ionic compound. This is to say that it's composed of two elements. Tertiary, which means we're going to have three or more elements, which necessitates the presence of a polyatomic ion. Again, something that you are required to memorize for this course, some of the more common ones. In this third type here, we have a metal, such as the case of iron, that can take on multiple charges, in this case the +2 ferrous form. So again, these tend to be transition metals, and we'll refer to them as metals that can take on multiple charges or multivalent metals. And there's this whole kind of naming convention that goes along with those. So let's jump right into binary. When we talk about binary ionic compounds, when we say ionic in the first place, it means that we're talking about a metal and a non-metal. The idea here is that metals have a very low ionization energy. They can readily give up an electron, whereas nonmetals have a high electron affinity. This is to say that they release energy when they pick up an electron. Recall, and we'll get into this in subsequent units, that the electronegativity difference between the metal and the nonmetal has to be greater than 2 for an electron transfer to occur. Again, the metal kind of giving it up and the nonmetal taking it. So just to recap, the metal is going to be the positive ion, given that it's losing an electron. We call this the cation. And the nonmetal is going to be the negative ion. And it's gaining an electron from the metal, and thereby becoming the anion, as it were. Okay. As far as the convention goes, it's pretty straightforward for ionic. Nothing super difficult here. We find that we are going to go ahead and name the metal first, and then we name the nonmetal second. While the metal retains its name, the nonmetal suffix actually gets changed. It becomes IDE. So in these two examples, pretty straightforward here. We have an ionic compound, again binary, metal, nonmetal, magnesium and nitrogen. Magnesium retains its name, but it's the nitrogen, the ending, that suffix, becomes IDE. We find the same thing in example 2 here, where lithium, again the metal, nothing changes, but it's the IDE suffix that gets added to our nonmetal, that second portion of our ionic compound there. Okay. So the question would be, what's actually determining the ratio of our metal to our nonmetal? Right? And the whole idea here is that ionic compounds are going to be charge neutral, that the sum of the positive ions, in addition to the sum of the negative ions, must yield 0. So in an example like AlBr3, you might wonder, why is it that aluminum bromide is AlBr3? Well, quick recollection, looking at the columns on our periodic table, if you remember, each column kind of describes the charge that these elements would take on in the event they ionize. So the first column is going to be +1, second column is +2. You kind of skip those transition metals for now. We have a +3, plus or -4, -3, -2, -1, no charge. So again, the column number can straight away kind of tell us what charge these elements will take on again when they participate in ionic bonding. So again, aluminum being in that third column is going to pick up a +3 charge, but it's the bromine that picks up the negative charge. Well, if we have a +3 and a -1, we need to find a way for this molecule, or this compound rather, to be charge neutral. So if one aluminum carries a +3 charge, we are going to require 3 bromines in order to get to a -3. And it's the sum of that plus 3 and the minus 3 that's going to yield that 0 there. So again, ionic compounds must be charge neutral. If given a name, so in the event I give you a compound like calcium phosphide, and I'm asking you to come up with the formula. The first thing we would do is we would be sure to look up those charges, right? So we'd find where calcium is in the periodic table. It's +2 charge. The phosphorus, the nonmetal, is going to be -3. So I always think of this in terms of, what is the smallest number that both these charges can go into in order to create the simplest ratio possible. And that number in this case is going to be 6, right? So we're going to need 3 calcium ions to get to a +6 overall, and then just 2 phosphide anions in order to get to a -6 overall. Again, these subscripts here denote the quantity of that specific atom within the compound. Okay, so that's going to go ahead and cover our binary ionic compounds. We'll move on to discuss tertiary ionic compounds, which operate kind of under the same principles, but again, they're just going to have 3 or more elements, which is to say that they're going to contain absolutely a polyatomic ion. And these things can be positive or negative. We're going to find that most of the ones we deal with in this class are negative. It's really just ammonium that we're going to encounter. It's going to be a positive cation, a positive polyatomic ion. So anyway, the way to kind of, recognize that there is a polyatomic ion present is that rather than that IDE, that "ide" suffix we saw a moment ago, we're going to see an "ate" or an "ite" suffix. And all this really kind of denotes is the relative number of oxygens present within these polyatomic ions. If we're going to see a polyatomic ion in a series, say oxygen teamed up with sulfur in a number of different ways, the polyatomic that contains the larger number of oxygens is going to get the "ate" designation, so sulfate, whereas over here we find that the "ite" designation is given to the oxyanion that has the smaller number of oxygens. Okay, so we have an "ate" and "ite" designation. Again, "ite" always going to be the lowered numbered oxygens. 8 is going to get the higher number, not necessarily 3 and 2. We might see 1 and 2, 2 and 3, whatever the case may be, in the way that oxygen specifically binds with some other element. Okay, the way that I kind of commit to this to memory is that if you ate, right, you are full, i.e., we have more oxygens present there. Okay, so when it comes to writing the formulas for these, nothing too crazy. Given kind of the following examples here, let's say in this first one we have sodium hydroxide. Okay, so we'd find sodium, it's a +1 charge. We have hydroxide, it's -1 charge. +1, -1, straight away they come together. Nice simple 1-to-1 ratio. In the second example, things may be a little bit more complicated here. Magnesium's a +2 charge. We have acetate with that -1. Because we already have a greater charge here from magnesium, we are going to need multiple equivalents of our acetate polyatomic anion there. Okay, so we're going to need 2 of them. And what you'll notice is that whenever we have a polyatomic ion needing multiple equivalents, in this case 2, we have to employ parentheses. If we did not employ parentheses, we might find that we have something like this, on our hands. If we need 2 acetates, maybe it looks like we got something like this. And this isn't going to be quite correct because it looks like all of a sudden we got 22 oxygens, which is not the case. We have 2 acetate ions there. Okay. On the flip side of things, if we are ever given a formula, all we merely need to do is identify what our cation and anion are. Again, very popular for our cation to be simply just a metal, in this case strontium. We look up our CO3, or again, already have that committed to memory, and we're talking about the polyatomic ion carbonate. Over here, it's that kind of 1 cation we're going to encounter. That's a polyatomic ion. It's that ammonium, carries a -1 charge, teams up nicely with the bromide, which is a -1 charge. Okay. And that's going to go ahead and cover tertiary ionic compounds. The last one, again, that you'll probably remember from your previous chemistry class, is what happens when we have transition metals. right? These multivalent metals that can take on more than one charge. In order to kind of distinguish between these, we have two different kind of naming conventions. So we have the ic and the us naming convention, which is kind of our classical or our Latin-based name. The ic denoting the higher charge possible, and the us indicating that we have the lower charge that's actually present. Or we simply use kind of the stock name, which employs Roman numerals. And it's this Roman numeral name that's actually a lot more popular in scientific literature these days, although the classical or Latin name is still used on occasion. Okay. So if we're given a formula, say FeF2, and we're tasked with naming this thing, we got to figure out what type of iron we have on hand. The way we do that is we figure out what is going on with our anion. So in this case, we identify that fluorine, or fluoride, carries a -1 charge, and there's two of them. So I kind of break this up almost into kind of two separate parts here, where the anionic side of our compound formula here carries a -2 charge. Well, because there's only one iron atom, or one iron ion, I should say, it must carry a +2 charge. So in determining whether it's the ferrous or the ferric, given that it's +2, it has to be this ferrous form. Okay, so we would write this as iron 2 fluoride / or ferrous fluoride. I expect both names, both the stock and classical, to be committed to memory there. Okay. Taking a look at a different example that contains iron, we find that this case it's teamed up with the sulfate, the SO4 polyatomic ion here. Sulfate carries a charge of -2. If we have 3 equivalents, that is to say that this whole side of our ionic compound here carries a charge of -6. Okay, which is to say this side needs to be +6. If there's 2 iron ions totaling a +6 charge, that means that each one must be +3. Okay, so we denote this again as iron 3 sulfate, or the ferric sulfate there. Again, the other skill would be to take a name and would be to construct a formula from that. Okay, so if we're given chromium 2 nitrate, not too bad. We're told what the charge is of the chromium straight away by that Roman numeral. It's +2. Nitrate, again, committed to memory, it's a -1. We're going to need multiple equivalents, namely 2 of the nitrate. So again, as we saw in that acetate example, we need a parentheses, CrNO3, 2. Over here, plumbous phosphate. Plumbous, we have the choice between the +2 or the +4 form of the lead. Plumbous is indicating that is, in particular, is indicating that we have the lower charged version of iron. So that's the +2 form. Well, +2 and -3 here, that lowest total we're looking for is +6 and -6. So our overall formula is going to be 3 equivalents of lead, 2 equivalents of the phosphate, so Pb3, PO4, 2. All right, that kind of tidies up ionic compounds nicely. Again, binary, tertiary, and then ionic compounds that contain multivalent metals. And again, those can be binary, or those could actually be tertiary ionic compounds. The big thing to think about is that charge neutrality concept, and just making sure the sum of the positive charges is equivalent to the sum of the negative charges. Okay. We'll push on and we'll begin to talk about acids. Acids kind of also follow some of the same rules as ionics, given that they kind of take advantage of this charge neutrality concept, but the naming convention is pretty different. Here we're tipped off that a compound is going to be an acid because it starts with a hydrogen. Okay, and we have 3 different types of acids. So the first type we're going to deal with is where the anion is monoatomic or ends with IDE. Okay, and the monoatomic is going to be a little bit more popular, but we will see some examples here in a second with IDE. So 2 kind of steps to this naming convention. The first is that we're going to use the prefix hydro, and we're going to change the suffix of our anion to IDE, or rather, from IDE to ic acid. So in this first example, you might see something like, hydrogen chloride. Well, again, we're going to ignore kind of that presence of the hydrogen, and we're largely just going to focus on what's going on with our anion. Given that this, again, is monoatomic, right? The anion's monoatomic. We have to use this hydro designation. So we go hydro, what would otherwise be chloride becomes ic acid. So hydro, chlor, again, instead of ide here, we have ic acid. So two kind of parts to this simplest form of acids where the anion's monoatomic. In the second example, we find that the anion is not monoatomic, but it does normally carry this IDE ending. So CN is the -1 polyatomic ion cyanide. So again, hydro designation, but cyanide gets changed to ic acid, so hydrocyanic acid. Two separate words in both cases here. Okay, so this is the first type, where again our anion is monoatomic. In the second kind of type of acids we're going to take a look at, the anion ends with an ITE ending, right? So this is going to be a polyatomic ion, and that ITE ending is just going to get replaced with is acid. So in this first case, we have HNO2. Again, we understand it's an acid because of the presence of the hydrogen. NO2 is normally the polyatomic nitrite. That IT ending gets kind of chopped off, and it becomes nitrous acid. Again, two words there. Given that we're no longer talking about an anion that is monoatomic, we will not use that hydro prefix any longer, okay? Here we have the ClO2. This is the polyatomic ion chlorite, kind of in that series of oxyanions. I think there are 4 of them that get teamed up with the chlorine there. The ite ending gets changed to us acid, so chlorite becomes chlorous acid. Again, no hydro prefix out front there. Okay. The last acid we are going to take a look at is when the anion ends with 8. So again, it's the second type of polyatomic we're going to see here. We simply change the 8 ending with ic acid. Ic acid. Okay. So the sulfate becomes sulfuric acid. It's the carbonate, that 8 ending that gets chopped off again and becomes carbonic acid. Okay. So again, we either have a monoatomic anion or something a little bit more complicated. We have a polyatomic there. That ite getting the us acid designation and that 8 getting the ic acid designation. Okay. If ever we are, again, tasked with kind of the other skill where we're given a name and we have to go ahead and write the formula, what we need to keep in mind is that the number of hydrogens is going to equal the charge of the anion. Again, I started this section by describing that acids are charge neutral. So if we're talking about phosphoric acid, ic acid is telling us that that ic is stemming from the phosphate polyatomic ion, which has a -3 charge. If we have phosphate, which has that -3 charge, we need to have 3 equivalents of our hydrogen ion in order to make this charge neutral. So we're going to have as many hydrogens as necessary to kind of balance out the charge of that anion there. In this case of chlorous acid, us acid is coming from ite, so ClO2 1-. This one's not too bad, right? If it's a -1 charge, this is to say that we're just going to need 1 hydrogen present. When writing compound formulas, we're never going to have 1. We have 1, but we don't write it in. It's assumed. So we'd write the formula as just HClO2. Okay? And that kind of takes care of acids. It's this third type that's pretty different from our previous 2. And again, so this is when we're going to see that the compound actually begins with a nonmetal. So we're actually going to have 2 nonmetals here. We call these things covalent or molecular compounds. The rules are pretty straightforward. The prefixes that they employ should be familiar, but if not, again, sorry. One more thing you're going to have to look to commit to memory. First off, the nonmetal doesn't change. Okay, so the name of the nonmetal doesn't kind of do anything different there. But it's the second nonmetal, and again, this suffix has actually become pretty popular, is we're going to get that IDE ending. Okay, now, given that these covalent compounds actually share electrons, it's a little bit harder to determine the ratio in which two nonmetals will come together in. So we need to have kind of a way to talk about quantity. And so to do that, we actually use prefixes, okay? And we use these prefixes to describe the number of atoms for the first nonmetal and the number of atoms for the second nonmetal. However, we will never use the prefix mono for the first nonmetal. So here, while there's one phosphorus, we're not going to say like monophosphorus. We merely just say phosphorus. We do have 5 fluorine atoms here. Again, not ions, atoms. And so that is going to get the penta prefix. So this compound here is phosphorus pentafluoride. Given these next 2 examples here, if we're given N2O3, now we are going to use a prefix because we have more than one atom of that first nonmetal. So we have dinitrogen, again, the suffix not changing, and then trioxygen. However, again, that ending of that second nonmetal is going to get changed, so it becomes "ide." So dinitrogen trioxide. And the second one here, kind of a classic example, we have the nonmetal and the second nonmetal, and both of them actually just have one atom. Again, no prefix, no mono prefix for that first nonmetal, yet we will use it for the second. Okay, so it's carbon monoxide. Again, that prefix telling us the number of atoms involved, just 1, and that IDE kind of going along with the rules of covalent compounds here. Okay. Besides that, you know, if you're given a name, something like sulfur hexachloride, because there's no prefix, we know that we're talking about just one atom. In this second portion here, chloride is coming from the atom chlorine, hexa indicating that we have 6, so SCl6. This wraps up the video for naming compounds. Again, we took a look at ionic compounds, acids, and also covalent or molecular compounds.